us to host Professor Don Pellet from Biden, Israel, to come to our university to give a mini course about software reliability methods. And I'll give a quick introduction of Professor Don Pellet. He got his PhD from Technion, in Israel from 1991, right? Yeah, then he spent like 9 years in Bell Lab. Then he works in including Austin, then Warwick in Verfication, then he moves to finance in Israel, and he's actually I don't think I need to introduce him too much because his name is quite big in the community of formal methods. He's a recipient of the CAB award, which is great honor of anything, and he's a pioneer in the verification of like partial order reduction, runtime verification, and he also wrote two very popular books, including model checking and software reliability methods. And this series of class was basically based on the content of his book, Software Reliability Methods. And you will see my name on the poster just because I need to pass the regulation of our department that if you make it as a class, then it should be a name of like a hosting professor, something like that. So basically, Don will do most of the teaching, and if you know any extra time, I will do that. So basically, that's it. It's for a very quick introduction, and let's welcome Professor Don Pellet.
Very much for the introduction, and I'm very happy to see a lot of people here. Do you hear me very well at the end? Do you hear me? Can you raise your hand if you hear me? You might not hear me. Okay. So first of all, I like this course to be interactive. So don't be ashamed to raise questions, to raise your hand, to ask me questions. If I'm too quick, please let me know, okay? It's not a trouble thing. I really want to be interactive. I also try to involve you in asking you some questions. Please don't be shy and try to answer. It's not an exam. Sometimes the question is not so obvious, and if you don't answer correctly, maybe because the question is meant to not answer correctly to make some point. So don't be shy, okay? It doesn't mean anything, and I think it's interesting to interact, okay? If it's okay, then please raise your hand. Okay, so I see we're interacting already. Okay, thank you. This course would be on formal methods, mainly about model checking and what are formal methods. I can shamelessly recommend two books. When I was born, I really wanted to write books in Chinese. And it happened that I wrote two books in Chinese. I was surprised that my books were translated to Chinese. I think it's a great honor for me. The first book, Software Reliability Methods, on which this series of lectures are based on, was translated by the group here, Professor Wu. And someone also translated the model checking book. I have no idea who this is. Some group somewhere. And this series of lectures will be based on these two books. I mean, one is enough, right? I think this is better for this lecture, and this is what getting there. Sorry? Okay. Sorry. Okay. So what are formal methods? Okay. So formal methods are techniques for analyzing systems, and they involve some mathematics. Okay? But it doesn't mean that the guy who uses that is a mathematician. It doesn't have to be a mathematician or a logician. It's just that there's some kind of mathematical basis or logical basis, formal basis for these systems. Okay? In fact, the best thing would be that everybody can use it, or someone that wants to develop systems, develop software, hardware, a combination of software and hardware would be able to use that, would be very intuitive. And in this little course, we try to understand some of the principles, but they should be very, very simple. Okay? So mainly formal methods include, well, there are three types of formal method. Now maybe there are four. The first one is deductive verification, where you want to prove that the system does what it's supposed to do. And in the early or late 60s, people started to look at how to verify that the system does what it's supposed to do. The motivation was that then, I mean, computers were very small and not very powerful, but somehow computers at the late 60s became very important. And one of the things was that a computer was kind of in charge of a lot of things in Apollo, in the spacecraft that went to the moon, right? And they wanted to verify things, and they had the idea that if you write software, it has to be reliable, and maybe there are methods, except for trying to test them and you know, just that people would look at them, that would guarantee that if you send some people to the moon, the computer is not going to kill them on the way. Right? So that, I think, was the motivation, but deductive verification is very difficult, because you have, you know, to use logical systems, and probably you have to be a logician. These are not so easy methods. You have to know a lot about mathematics. And then, at the beginning of the 80s, two groups. One was led by Ed Clark, and another one was led by Joseph Sifakis. Ed Clark in the US, Clark and his student Emerson, and Sifakis and a guy called Gray developed simultaneously, concurrently, or I mean, they still argue that maybe one was influenced from the other. We don't know. I mean, there's lots of wars about that. But both of them, both these groups, developed what we call model checking, which is the automatic verification of systems. Okay? And this is the main thing that we would look at this mini course. What we really want to, don't want to use logic. We don't want to work hard to have a lot of insight about the mathematics. We want to somehow check what we want automatically. We don't almost press of a button, and we find if there are errors. We find counterexamples that would help us to debug the system, etc. And in fact, the oldest method, which I don't think we'll have enough time for that, is testing. And testing used to be very informal, so there are all kinds of ways of doing testing, like programmers exchange the code between the groups and you know, look at the code, do what is called walkthrough, which is like a hand simulation, or just raise all kinds of typical concerns, like whether someone keeps a I don't know, a pointer goes missing, or you use a variable that was not defined, etc. There are lists of hundreds and hundreds of these cases, but nowadays testing and model checking, they kind of influence each other. So testing become more formal and more exhaustive in some way. And model checking also learns from testing, and sometimes instead of doing exhaustive model checking, which means that in some sense you check systematically all of the behaviors, instead of that there's like statistical model checking where you find all kind of probabilistic or statistical results about the system. So far it's just introduction, there's nothing very complicated about that. So if we want to apply formal methods, or we want to develop formal methods, there's lots of questions we can ask ourselves. What techniques we want to use, which tools, do we need experts? What kind of experts? Do we need to train these experts? What are the limitations? One of the important things that we learn is that each formal method that we use, like model checking, has its limitations. You cannot guarantee everything, etc., etc. It doesn't matter much to go over all this list, but there's lots of concern. So before we start to talk about one particular formal method, which is model checking, let's see some concerns. So people say some kind of bad things about formal methods. For example, people say that formal methods can be only used by mathematicians. Okay? Some people say, I mean, it's formal. So, you know, I want to hire some programmers from Microsoft. Do I need to hire logicians and mathematicians? Or is it to the point? And other people say, well, if you do verification, the verification itself would be erroneous, right? So if I use, you know, term prover, or I do hand term proving, or I use a model checking tool, maybe there are bugs inside the tool itself. Maybe my proof is wrong, right? Who says my proof is correct? And another thing that people say against formal method, and I have to say that these I heard myself when I work in Bell Labs, and we try to make the developers use our methods, is that if you use formal methods, it's more work and it would slow down projects. Right? And of course, since I'm teaching that, I have some answers. So the first thing is that, as I told you at the beginning, formal methods are methods which are built on top of some mathematical, logical, computer science principles, but the user should be able to. So it's one thing to develop them and understand how they work, another thing is to apply them. This is true. You cannot verify anything completely, right? There's many philosophical reasons why you can't, right? If you verify code, okay, maybe there's errors in the verification. Maybe there's errors in the tools. Maybe there are errors in the hardware on which you run your verification tools. There's all kinds of things. Maybe you verify the code not directly but you kind of translate it into something that the tool allows you to do, and the translation is not correct. All kinds of things. But the main thing, the use of formal method reduces errors. If it reduces errors, then it's good, right? So we don't set up our goal, you know, too high. We actually benefit because a lot of companies use it. I mean, I think any hardware manufacturer, Intel, I don't know, ARM, they all have big formal methods group, and they all use methods like the method I'm going to show you. And about slowing down, I would just refer to one experiment we did when I worked in Bell Labs. They said, really, you know, you want us to use your methods, but we need more people, we need to train them, we need to have time. And we made some experiment. Two groups developed some code. One used formal methods, or actually exactly the one I'm going to show today. And the other one did not use it. And we said, let's see what would happen, okay? So in fact, that didn't slow down the project. The only thing is that the group that used the formal methods, it found some problems, okay? And it had to report to the other group, because otherwise, at the end of the experiment, one of the group was just, you know, lose all the time because they were doing something wrong. So I think it would speed up projects, because the fastest you would find errors, okay, the fastest you would correct them. If you have to correct them in a much later stage, then you lose a lot of time because you have to redo a lot of stuff. Okay. Let me not go over all these philosophy here, and let me go a bit more directly into the technical stuff. So we want to verify systems. And what kind of system do we look at? We look at actually any kind of system. So the system we want to verify is either sequential, concurrent. There will be several processors, but maybe with the same memory or mutual memory. Distributed system, there could be communication network, or there could be systems that involve different kind of locations of the internet, but it's one system. and we want to verify the entire system. It could be reactive in the sense that the system could get all the time inputs and have to supply outputs. It has to interact with its environment. This could be communication protocol. Abstract algorithm means that it could be, say, an algorithm that calculates something mathematical. It's not connected or restricted to a particular, say, word size in memory. It works on any integer or whatever. And in particular, we are going to look at, and that looks like a big limitation, but usually it's not finite state systems. Finite state systems are systems where they can have only a finite number of states. That's why it's called finite state systems. And you can think, oh, well, that's a big limitation, because say, if I need to find the, I don't know, the sum of two numbers, or I have to find the least common denominator of two numbers, okay? The least common denominator algorithm does not work on finite state system. The algorithm works on any numbers, right? So why work on finite state system? Problem is that a lot of time the problem of verification is too difficult. It's undecidable, in fact. But if you can look at a finite state portion, then it's decidable. You can do some search. You can do something which is exhaustive. So the technique which is called model checking, for many cases, is confined to finite state systems. Okay? So if you want to verify an algorithm, in general, maybe it's undecidable. Maybe you cannot do that in general. Finite state system, you can do, and we would look at finite state system for most of this later course. Okay? So, if we have finite state systems, what we want to do, we want to verify them. And if we want to verify them, we want to verify them against something, right? So we want to give it a specification. So in the old days, you would take some kind of a book which includes all the requirements, and you try to see if the system satisfies these requirements. But that's not very formal. So we would look at some formal ways of writing requirements. I hope you can read the yellow, which in this case would be like a formula. It would be something written in logic, and we're going to learn that logic. It's a logic called temporal logic. Logic that tells you how things change in time. For example, here it says that x is between 1 and 5 until x is 7, and then from that point on, x is always greater or equal than 0. Okay? This is a formal specification. If the specification is written in a formal way, then you can verify against it. Okay? If it's written in like a language like English or Chinese, then maybe you have different interpretations. But if it's written in a logic like here, then it could be correct or incorrect. And there's only one interpretation. Here I wrote the same property as an automaton, and we learned that as well. It says that at the beginning, the value of x is between 1 and 5, then it becomes 7, and then it stays greater or equal than 0 for the rest of the time. Okay? And these two specifications are actually equivalent. So we're going to learn these two kinds of specification formalisms, and that would help us because if the specification is written either as a logical formula or using an automaton, then we can develop algorithms that will check against that. In fact, to give you a clue, kind of a spoiler of what is going to happen, is that maybe it will be more intuitive to have the specification written as a formula and then translate it into automaton and then develop an algorithm on graphs. Okay? So, as I said, for finite state machine, I'm going to apply model checking, which is the main thing that we learn. Or, if it's not finite state, we can apply deductive verification, third proving. That usually is undecidable. That means you need a logician or a mathematician. This is hard. I mean, you can have some support from programs, but it's undecidable. So it's a lot of work. Okay? And if the program is too big, if the program is too complicated, sometimes you want to apply testing. And sometimes the best thing is to apply combination of all of them. So that kind of, you try to work as little as possible. So you choose the method with the least work, but you combine it with other methods so that the guarantee would be the maximum. Okay? So sometimes you have to compromise because you cannot get everything you want. You would not guarantee full correctness, but at least kind of you see that you use several tools, and as far as you know, it's good. So this is to be practical. Okay, the first thing we need to do is to model a system. So there would be three things. Suppose someone gives you a system and he says, this is the system I developed, I want to check it. I want to do model checking, or I want to verify it. What do you need to do? So there would be three important steps. One of the steps would be to model it. Okay? We take that system and we pass it into some kind of representation which we can apply algorithm on. Okay? The computer would understand it. Okay? I mean, a program is something that we can apply an algorithm, right? The program, you use compiler and you get some kind of representation. But sometimes a program would be too big, or the model checker would not understand that programming language, or it would be too complicated. Okay? Also, if you use a compiler, maybe you get some machine code, and it would be too complicated to do stuff with. So the first thing is to do modeling, to take the thing you want to verify and to construct a mathematical model which will be concise, will be small enough, but it will represent the properties you want to verify. Okay? I mean, why do we do modeling? I mean, physicians are used to do modeling. They want to say something about the stars, okay? They want to say something about, some physical system. Either they're big, like the stars, or maybe they are like subatomic, okay? So usually what they do, they don't go and measure the stars, and they cannot even, see the electrons, right? But they build a model, right? They build a model and they bring what they do into the size that they can handle, okay? Whether the model and the actual system are the same, this is a good question, right? So we assume, right? So we assume what we know about the stars is correct, right? It kind of is consistent with our measurements, right? So in the same way, the model should be consistent. Of course, we have no guarantee. If someone is doing the modeling and the modeling is not correct, what it would verify is the correctness of the model. So if there's a discrepancy, that would be a problem. Okay, so we have to remember, I said at the beginning, verification cannot be foolproof, right? So one of the things is that what we verify is the model, and it is as good as the model is. But let's assume that we do the modeling correctly. Why I'm saying that, you'll see that we, as the people that apply verification, are an important factor in the modeling. If we look at the system, there are all kinds of decisions of what things we want to see, what things we want to ignore, or we have all kinds of choices how to do the modeling, and a lot of things depends on us. After we do the model can be used for the verification, and then it would be automatic. But it's important that we understand the system correctly. After we did the modeling, we also need formal specification, right? So we need something written in a logic or using an automaton, like I showed in the previous slide. Is that microphone really works? Because I can hear myself like not smooth. No? It's okay? Yeah, okay. Okay, so I need a model. I need someone that would write for me the specification in a formal way, not in a book, right? Not in a book, not in a natural language. It has to be written in a notation like automata or like logic or a visual notation, okay? And then after I have that, then I can do the verification. The verification or the model checking, if it's good, it would either say to me, yeah, I didn't find any error, or it would give me something like a counter example. Look, this is a behavior that does not satisfy your verification. That would be very good, because I can go back to the programmer or the system developer, and that helps me to fix the system. Okay? So there's all these stages. Okay. In the book, if the Chinese version has the same chapter numbers as the English version, this is chapter 4. Okay, I want to do modeling. There's all kind of modeling languages or formalism. I'm going to use a modeling formalism that is very, very simple, and it will capture everything. By the way, for all of you who take pictures of the screen, you'll get all the slides, right? So you can find the slides. They are available to you, right? There's no need to. Okay, let me skip that. So I want to model the system. Let's see. I mean, I want to see if we interact well. So I have a system, okay? I have a system, and my specification is the following. You have to answer that. The system at the beginning, it gets some input. The input is a vector of n plus 1 places, between 0 and n. Okay? And these are integers. Okay? And at the end, the program does something. At the end, the specification says that for every I, the value of AI is more or equal than AI plus 1. That means that for every adjacent pairs, the element with the higher index has a value which is bigger or equal to the previous. Okay? This is the specification. See, it's not written in a natural language, it's written in a formal language. Okay? Someone wrote the specification for me so that I can apply maybe a model checker or a theorem prover to that, and I can prove it. What does this program do? I have a program, this is what it's supposed to do. What does it do? In natural language. This is interaction, so anybody can think what is the purpose of this? If I didn't say that this is the input and this is the output, what should you do? Yes? It's some kind of sort. Very, very good. Yes, thank you. Thank you very much. So the program is supposed to sort, okay? That was a trick question, okay? That was the goal of the program indeed. That is the correct answer. But this is the point. The point is, if I'm the person who's doing the verification, okay, I have certain points of failure. One of them could be modeling, and one of them could be the specification. So this is exactly an illustration that shows you that me, as the person who moves the actual system into a model and a specification, can have some problem. So there's a problem here, because I'm saying that if a program satisfies that specification, it's not necessarily that it does sorting. Although that's what the program is supposed to do. That was a correct answer. Now, why it doesn't have to do sorting? You have to answer. I have to answer. Okay? Can you see a way that there's a program that's going to satisfy this, but it's not going to sort the array A? It's a trick question. How can I satisfy that goal without sorting the array? Yes?
we just set the numbers.
Sorry?
We set the numbers.
Yeah. So I can satisfy that specification. Specification is correct. It is a specification for a sorting program. It's not complete. Okay, there's something missing. And the missing part is to say that the values at the end in the array A are permutation of the values at the beginning. I didn't say that. So if my program just sets 0 to all the elements of A, or any random numbers which are going to be ascending, it's going to satisfy that, right? You see that? There's no, I didn't claim that the A is at the beginning. I mean, I could just say the program could do for every AI equals A1. So I just put the first element into all the other variables. And indeed, I get a non-descending series of numbers, right? You see that? What we learn from that? When we write specification formally, as opposed to natural language specification, as opposed to directly combining things, kind of there's the man in the middle, or woman in the middle, that is responsible for a lot of things. So, we want to represent programs of concurrency. Concurrency is not easy. I mean, how do you represent things that happen at the same time or independently, okay? So we're going to see, it's not complicated. It's a bit frightening maybe at the beginning, but it's very easy once we get kind of the intuition of it. And one of the things we want to ask is what is the granularity of transitions? So the system is advancing, okay? And how do we present that the system made a very, very small change that is inspectable? We are aware of that change. It affects the property that we want the system to have. It affects the correctness, but it's not too small. Like, we don't want to verify the system on the level of, the clock of the system, which, ticks every, ticks like in 2 gigahertz, right? That's too refined, okay? And if it's a concurrent systems, do we look separately at the processes, or do we look at the global state of the system? So let's dive in. In order to do the modeling, I would present a very simple model. It's going to be called the interleaving model, and the systems are going to be called transition systems. Oh dear. Just a second. It's going, and we have the following components. So the first thing is I would assume that these are very simple systems, and I have variables that would include data. So at this moment, I'm going to ignore that I have arrays and message queues. Everything is stored in variables. This is for simplicity. I can represent any data structure. And I have variables v0, v1, v2, etc. I have a number of variables. Usually it's a finite number of variables. And each one of them would have its own domain. So a variable could be an integer, a ring, okay, a character, maybe a string. I have some variables, okay? Now, in order to say things about the system, I'm going to use predicates, okay, or a parameterized assertion. And these would be sort of a first order formula that would say the connection between the variables. Here, I say that the variable 0 is always the sum of v1 and v2, and the variable v3 is always bigger than 4. So I have variables, they have values according to their domains. And so any assignment of values to all the variables according to their domain would be called a state. For example, if all of them are integers, then v0 could be 1, v1 could be 3, etc. Right? This is a state. State is an assignment of variables, of values to variables according to their domains. Okay? And the system could be in different states. So it's like if I want to verify a program, the program is running, and if I stop it at some point, I look at the memory, and I suppose that it consists of variables, or I can look at every variable, there would be some value. That's the state, okay? And I can say that state either satisfies a property or not, right? So I can say I can ask whether this state satisfies that property. Because V0 is V1 plus V2, V0 is 1, V1 plus, oh, I didn't have V2 here. So yeah, I don't know here, but here I have an example. P, the predicate says X is bigger than Y is bigger than Z, so I have this state. 4 is bigger than 3, but 3 is not bigger than 5. So this state does not satisfy this property, right? On the other hand, if here I have 2, then it would satisfy that property. So a predicate like that actually partition the states into 2 groups, or 2 sets. Those that satisfy the predicate and those that don't. Okay? It's okay so far? It's very simple. So I have variables, I have states which are assignments to these variables, and I can write predicates or parameterized assertions which would partition the states into those satisfying and those that do not satisfy. In the state space of the program are all the possible states, are all the possible assignments to the program variables. Okay? Again, I can partition them according to some predicate. Okay? So if I have the variables A, B, and C, and they could be integers, then the state space is all the assignments of integers into these 3 variables. In this case, the state space is infinite, because I have infinitely many numbers. So I have states. Now what I need to tell you is how I operate in states, how I make a change. Now the computer is going to run. In my model, I make a small step. I want to model the very small steps that I can look at, but not too small, otherwise the complexity would run very high, and maybe it's not on the level that I want to look. So I need to define transitions. These are the smallest actions that I can observe, that I'm interested in observing, and they would be called atomic actions. Why are they called atomics? Because for what I can see, I cannot separate them. If, say, I have 2 atomic actions, and they run on different processors, they run concurrently, okay? Then they would behave as if they execute completely, one after the other, in some order. It doesn't matter which order, but one after the other. It wouldn't be possible that they would affect each other in a way that corresponds to one of them execute halfway and the other one starts to execute, right? There is no influence between parts of an action. That's why it's atomic. Okay? Atomic in the sense that you cannot split it. Right? You cannot observe that you split it. Okay? For example, if I look at this assignment, and I ask myself whether A equals A plus 1 is atomic, okay? It's a good question. Should I model things in a way that A equals A plus 1 is atomic? Okay? What do you think? Is that an atomic action? That's the level of granularity that I should look at when I model a computer program? Any answer is good here, so you should answer. Any answer is good. There might be interruptions, right? Why? That's true. Yeah. Okay. So any answer is correct, but his answer is also complete. So I would not look for further answer. Yeah. So the thing is, you might be able to break that. Okay. And if you break that, if you do say 2A equals A plus 1 in 2 programs, and they run concurrently in 2 processors or 2 threads with the same memory, maybe that could influence each other such that it does not look like you execute one of them before the other or the other before this one, but there's some interaction of parts of it, okay? It doesn't have to be like that, So that's exactly the same problem as in my specification of the sorting before. It's up to you, the person who's doing the modeling, it doesn't mean that someone is actually doing the modeling, but someone is deciding on which program would translate the actual system to a model, or someone writes the model checking code itself, right? So whoever is responsible for that, he has to at least understand what are the choices here, and that there are several choices. It could be that A equals A plus 1 is atomic. In fact, I don't know how many of you understand the C language, C programming language. Only you. That's why, no. Ah, a lot, right? No, not a lot. Hey, what language you learn here now in China? C. Okay. Next time I'm going to ask negative. How many doesn't know? Okay, in the C programming language, you can write something like, you can define a variable, say int A, right? But you can say, I think it's register int A or int register, I don't remember the order. In that case, it's kind of a recommendation to the compiler that if it has enough registers, A would be in a register. In that case, I would bet that if you do A equals A plus 1, it would be done atomically. The hardware of the machine would make sure in hardware, right, that if you do 2 increments to A, right, and in 2 processors, right, it would be, I mean, I think I can find it hard to believe that they would share a register, but if you didn't say it's a register, then what he said is may happen, because if you do A equals A plus 1 in process P1, and also in process P2, then usually it's translated to machine language, right? And in machine language, here is assembly, you would load A to some register, you increment the register, and you store back the increment value, right? So you translate both of them, and now let's look at what the 2 processors do. And they do this. The first one loads a 0, right? Now they kind of, the left process, P1, is kind of working semi-concurrently with P2, because there's some synchronization. But they interleave, like, oh, I take this action from here, and at some point I take this action here. So I load A into R1, and after that, I load A to R2. So the execution goes like that. This is the order of time. Okay? Let's assume that they interleave in the sense that really they do one action at a time, although they could actually work concurrently. So I load A, I have R1 is 0, I load A to R2, it's 0, 2, I increment R1, I increment R2, both of them are 1, and I store A, and I store A again, and I increment it only once, right? This is exactly what he had in mind. Okay? So, my responsibility to model correctly, at least not, to manually model, but to apply some program that models, and I did not model correctly if I assumed. Let's look a bit more into this example. What I'm trying to do now is trying to build some intuition about modeling. Because modeling, again, if we talk about, the stars or something which is subatomic, it's a model. I mean, I think, I heard, for example, that what we know about matter, about subatomic things, is probably 20% of what there is, right? There's 80% more that we don't know about matter, right? There's a lot of questions. If you go to CERN, you see there's a lot of problems which are unsolved, right? So it's a model. It could be correct or incorrect. Our responsibility is to make it, correspond as much as possible with the actual system. So let's try to see what kind of assumptions we make about modeling and why they're probably correct. Okay? So here again, I look at this execution. This time, I did not assume that actually things happen in a sequential order. Sequential order between concurrent systems happened, I think, before you were born. Many years ago, there were not really concurrent programs or concurrent processes, but there was something which was called multiprocessing, where every program had a chunk from one main CPU, and they thought they are concurrent, but actually they interleave. They share the same CPU, right? So there was an order, but nowadays most systems have concurrent processors, even on the phone, right? There's 8 processors usually, I think. So they are really concurrency. But let's say this is happening, that happening. These are some variables, and part of these things could happen concurrently. For example, I maybe assume that since this action actually accesses A, and this one accesses A, then probably there is an order between them, because probably the hardware will not allow to access the same place in memory at the same time. So probably there would be some prevention of concurrency in hardware. But probably incrementing of R1 and incrementing of R2, because these two processes could happen concurrently, partially or totally overlap, independently. I don't even care about what order. And probably again, I have some order between the stores, again, because this is A. So I hope you can see the green lines. You see the green lines? So the green lines correspond to what we call causal order. What must happen before what? So there is a total order, there's a causal order in one process, because the process is sequential, right? So I load, I increment, and I store. I load, I increment, and I store. And maybe there is some order because of the access to the same variable, here and here, here and here. Okay? This is the causal order, but I don't care the order between this and that. Maybe they are partially overlapped. Okay? Now, how am I going to model it? I want a simple model. This is not very interesting. Let's see what happens during time. Okay? If really this action has to come before this action, then this probably terminated before that, right? That's prevented. I mean, the concurrency is prevented by hardware because I use the same variable A. But this increment and that increment, they partially overlap. If the time goes kind of from top to bottom, then there's partial overlapping, right? And now this has to end before that starts, because again of the causality. Okay? So there's some order which I give. Maybe I'm also interested about the actual time. Maybe I'm interested that between load and store there would be 2 microseconds. Okay? But maybe not. In most cases, I'm not interested in the time. I'm only interested in the order. Okay? So one simplification I can make is that I would assume that I look at the points where something ended. So here, okay, this is the beginning of the execution, and here that load ended. And here, that load ended. And here, well, here I started incrementing. Okay, this is not so good. I should have had a line here. Somehow, I forgot. I think the line from here has to move here. And here I have that increment ended. Here I have that store ended, and here I have that store ended. Okay? Just this line should have been here. Okay? And what I can do is now let's see at every point in time, instead of the line I wrote the points in time, I write what are the values of the variables. At the beginning I know that A was 0, I don't know the value of R1 and R2. After I loaded, R1 became 0. After I loaded here, R2 also became 0. Now, things that did not change, I just keep them the same. Okay? I think it's a nice model. Let's say, it depends at what level you want to look at the system. But I would say for 99% of the cases, this is a good enough model that represents what happened. So I would consider these actions. You see, between every 2 states, between every 2 subsequent states, there is an action. And I consider these are the states of the system. Of course, this is completely imaginary, right? Because you can say, well, let's go back here. This is the state of R1, which is only in that process, and this is the state of R2, and A is combined. But here I have global states, right? I combine what is the last thing I know about that process and what is the last thing I saw about that process. This gives me a global state, as if I stop the system and I look what are the values. And this is the level in which I want to look at things, okay? This is completely, I mean, until now this is complete, 1 minute, so I think we need to give a break, to get a break. But this is completely philosophical. But this is a model which I want to use, and it's a simple enough model. We think that the system does atomic actions, and each time it does one atomic action, it changes the state. This is simple. I would say 99% of the times, this is sufficient to say what you want about the program. Okay? The reason I saw all the other stuff is that because kind of I think it gives you intuition what is the relation between this model and how the things actually are executed. And now we'll have it.
现在10分钟的茶歇，大家可以休息一下。
不然会被人抢在位置。
本系要学分的研究生和大四的本科生务必签到，因为你们那个签到的这个记录我要交给教员，是你们拿学分的依据。然后外校如果外系的同学没有学分要求的，也去签一下到，因为有可能你们是属于前面注册的，会有证书，就是送的那个。然后他的 PPT 我们会在今天或者明天会建一个个人群，然后丢到那个群里面。暂时先来这些，这些有什么要未通知要求的同学，另外这边注册一下，我们会另外再看，自己开，因为之前没开会的。
But you're absolutely You're right. What you said is common enough. That something is not. This is sufficient to understand the process. If we want to verify
他说这个课没考试，只有辅导。
Okay. What I want to say is, this is probably the actual thing. It takes time, but in fact, there's two models.
随便说可以，但是他明年就不认我。不行，因为你现在不行。你考到吗？你是否研究9月之前？陈燕现在说可以，但是到时候他认不认我？不是，这个课它不是一个类似的，对啊，以前说的，我们在分析就是你要
How do you spell this system? I'll tell you. No, it's not. It's not. You have to check once. Okay. So, actually, in the break, someone came up with some very insightful comments. I share one of them with you. He said the following. He said, okay, look, this is actually probably what physically happened, right? That, this is what physically happened. But in fact, all I know is that there's some order. I know that this action happened before that, this before that, and every process is sequential. What he said is that how do you know what is the order between this and that? And in fact, I don't. Maybe I didn't even measure it. It's not something that I'm concerned with. And he asked, can it be that actually this increment happened or terminated before that? It could happen, okay? So for this same thing, maybe what happened is that the state here, okay, and later the state here is not the right order, but it's first the state here and that after that state, okay? So maybe the order of these two is reversed. Maybe after a state of R0, R1, I have 0, 1 here, right? So I'll switch these two orders. So I have two interleavings that corresponds to the same partial order. It's only a partial order between these elements. They're not in order. And he was right. So if he understood that, then he knows quite well. So you see, this is just a model. In this model, if I ignore the actual time, and I don't know the order, I don't care about this order, there are going to be two interleavings here, which are consistent with that partial order, and it could be that, in fact, increment R1 happened before increment R2 happened before increment R1. And so here I have R1 is 0 and R2 is 1. I have two interleavings, and they correspond to the same knowledge I have on the actual execution. Okay, that's again, it shows you that the model is something which, it's something conceptual. At the end, you have a way of modeling things, and what you verify is you verify things about the model, and it's correct about the actual code if the model corresponds to the actual code. In the case that you really don't know or don't care about the order between these two, actually you have two interleavings, two total orders, and they're kind of equivalent. If the specification is not crazy, then the specification would not distinguish between these two cases. And if you check all the executions, okay, then both would pass or both would fail. If the specification distinguishes between these two, it would be a bit weird. Okay? But it shows you that at the end, this is a model, right? And you can ask yourself questions about what corresponds between the model and the actual execution. And these are good questions. The thing is that you should kind of convince yourself that if you verify something about the model, then it's going to carry over to the program. Again, convince yourself in the sense that as you prove things about what happened inside the atom, right? So it's consistent with experiments, but you don't, it's a model. Okay, so let's move on. So we have states. We talked about transitions that are atomic, and now we want to represent atomic transitions. And the representation will be the following. Each transition, so if I want to represent load or increment, and if by chance my A equals A plus 1 is atomic, if it was by chance atomic, or anything, is represented in the following syntax. Okay? This is a transformation. It has two parts. The left part, left to the arrow, is the condition. It's the enabling condition. It's the condition for the action or transition to execute. If that condition holds, then the transition can be fired, can be executed. If it's not, then it cannot be executed. Okay? That's the condition. And on the right, there is some assignment. If the transition is executed, then the assignment takes place. My assignment looks like that. It's a bit more complicated than a simple assignment. Here I have a list of variables. And here I have a list of expressions. What happened is that I first calculate all these expressions. These are simple expressions, right? This is the value of D and this is the value of C. I first calculate all of them, and then I assign them in corresponding order. So the D goes to C and the C goes to D. Why I said that I first calculate all of them and then I assign? Because if I assign them one by one, D goes to C, then C now is equal to D, goes to D, then I copy D to both. If I first assign C to D, and then D to C, but D has the value of C, then, right? So what I really wanted is to switch between C and D. So I first calculate all of them, the old values, and then I assign the old values, okay? This is important. Now, this corresponds to an atomic action, nothing else. This is the only thing I need to represent actions. And so that would represent anything atomic in the program or in the system. And you can ask me, oh, look, you talked about atomic actions, and you said that A equals A plus 1 is not atomic, may not be atomic. Okay, it depends on the action system. And now you allow this thing, which is a multiple assignment. So in one atomic action, you're going to do both checking and assignment to two variables, right? So, you know, what happened to you? You're not consistent. So can you think about why I need this complicated stuff? Because I hint, look at, you know, the most trivial thing that happened in the computer, right? So there's some kind of a machine language action, right? The transition, assembly command, fires. What does he do? What can he change? Can he change two things at the same time, like in atomic time? I would answer that. And the answer is yes, usually. Why? Because in this model, everything is in variables. One of the variables would be the program counter. The program counter is important because the program counter allows the program to work in sequential order, right? Unless it has branches, right? So if it was really a counter, we say program counter equals program counter plus 1, unless it has to switch, right? So this is one variable. And one of the conditions for the program to fire is that the program counter points to the label of that command, right? But it could also depend on other things, like if there's an if it checks from some variables, it's a wait command, okay? So it has to check for things. And now, the multiple assignment now, why it has to be multiple? What two things it could change? So one of the things that you know, assembly command can do is, I don't know, it can change a register, it can change a memory location, and the other thing it can change is program counter. Program counter is also a variable in my model, and therefore I need the multiple assignment, although usually the assignment would be very simple. And this is done atomically. However, the computer guarantees if it's not done atomically, then things would not work. Okay, and another thing, the last thing I need to represent my model is the initial condition. I assume a predicate. Remember, a predicate is some assertion with three variables, right? The initial condition would be a predicate that would say what are the initial states. The program would start satisfying what, right? So here it would start with A is bigger than B, B is bigger than C. Usually it would start at the initial location where the program counter has some initial value, right? They point to the labels. So now I have a transition system. We solved that. I have a finite set of variables, each one over some domain, usually. In my case, for model checking, finite domain. I have a set of states. Each state is an assignment, right? Of variables to values according to the domains. I have a finite set of transitions. Each transition consists of an enabling condition, the condition for it to fire, and the transformation, which would be a multiple assignment. And I have an initial condition. This corresponds to everything. Oops. this corresponds to everything, which is nice, because I would be able to model this thing, everything, including concurrent programs, right? So because I have the program counter as part of my set of variables, I'll be able to take transitions of different processes, and I'm not going to distinguish different processes, it's just they're going to be dependent on different program counters. And that would be sufficient. We'll see an example of how simple this is. That takes all the structure of the code. The code could have loops, and could have concurrency, and whatever you want, and you put just a simple set of transitions of that form into one column. It would execute according to the original semantics of the code. I think this is good. So let's see. Here I have a very simple program, and at the beginning I don't have a program counter for simplicity. Let's see, this program has 5 variables A to E, and all these variables, they get natural numbers. So let me even, they get natural number. I include 0 as a natural number. Some books say naturals are for 1, and some say 0. I assume it's starting with 0. Okay? Every variable is natural, and I have 2 transitions. There's no program counter, so we start without program counters. And the condition to execute the first transition is that C is bigger than 0. And what it does this multiple assignment. It's going to decrement C and increment E. This one checks that D is greater than 0. It's going to decrement D and increment E. In any case, it increments E, and in any case, it decrements something, either C or D. Right? In some sense, you could say it moves a 1 from C to E. Here it moves a 1 from D to E, and it does that as long as C is bigger than 0, or as long as D is bigger than 0. Notice that these are natural numbers. They're not reals, or they're not reals, or complex. Natural numbers. You good? Now, the initial condition is that C equals A, equals B, and E equals C. I don't know how many of you would already say what this program does. Can anybody say what this program does? It does something very simple. Well, you would think, well, I'll keep explaining it. So one thing is that this program does something related to the initial values of A and B, okay? And the result is in E. And we keep giving you hints. A and B, and the result is in E. Now, it uses the value C and D. What it says is at the beginning A equals C and B equals D. And the reason it does this seemingly complicated and maybe seemingly useless thing is that it wants, the specification wants to relate the value of A and B with the value of E. So since I'm going to change C and D and I want to do something, E is a function of the initial value of A and B, what I did is I kept these values of A and B. Instead of changing them, I kind of said that C and D have the same values so that I can claim about the relation between E and A and B. If I say something at the end about the relation between E and A and B, it would be the same values as A and B at the beginning because they don't change. The motivation is the specification before. Remember that I didn't keep the relationship between the A values at the beginning and at the end? Right? I needed somehow to say something about the beginning and the end. Here, I took care of it because I didn't change A and B, and so if I say something about A and B at the end, it would be the same values as in the beginning. Okay? And I can work on these values by copying them to C and D. Logic. Here, E is a function of A and B. Okay. I'm not going to kind of fill the room with words. You really have to decide what that does. Anybody? Sorry? Yeah. It sums it sums A and B, right? In fact, it sums C and D as well, but C and D would change, right? At the end, there would be 0. Okay? Now, transition systems. And student here, he knew what he does, but in fact I didn't tell you something. I didn't tell you how to form an execution output, right? Now I talked about my model. My model was called the interleaving model. And the interleaving model assumed that at any point, only one transition was fired. Okay? Although, as I showed you the intuition, maybe some transition happened concurrently, but I chose them in an atomic way such that in some sense it is equivalent to having one transition in a time. That's why I could use the interleaving model, right? So everything I think now fits together, right? Transitions are atomic, and I can use the interleaving model. It is simpler than the model which looks at, the execution, which kind of, took time into account, or there were some transitions that were in the middle of execution. I can, I'm assured because the transitions are atomic that the execution could be the interleaving model. It would correspond in some sense to what I want to know about the system. If I convince myself of that, then I can define what an execution. This is kind of very formal, but it's very simple. What it says that an execution is a sequence of states. Right? S0, S1, S2, etc. The first state, it's an initial state. It's a state in which the system can stop. So the first state has to satisfy the initial condition. Okay? So far, so good. Now, if I want to move between one state to the next one, its successor, then I can do that by firing a transition, by executing a transition. Okay? What does it mean I execute a transition? Suppose I'm in, say, S1. I have to pick up a transition. In order that it would be executable, it needs to be enabled, right? So I need to check if the condition, if the enabled condition of that transition is satisfied. Remember we talked about this predicate. Initially, the enabled condition and the initial condition are just predicates. So I can check if a state, if the current state satisfies them or not. Remember? Every predicate partitions the set of states into those that satisfy or not. I take a transition, I look at the current state, I check if the current state satisfies the enabling condition, then I can choose a transition. It could be that I can choose several transitions. Several transitions would be enabled at the same time. I choose one of them. Okay? I choose any of them, and I apply the transformation. I do the assignment. Based on the values of the variables in the current state, I get a new state. And that's the successor state. That's it. I keep doing that. Doing it, and there are two choices. One is that would be an infinite execution. And the other one is that at some point there are no enabled transitions, so it has to stop. My execution is maximum in the sense that as long as I have at least one transition which is enabled, I have to continue. Either it's infinite or nothing is enabled. When no transition is enabled, there are two names for the situation where no transition are enabled. It depends that if you're happy about that or not. If you are happy about the fact that no transition is enabled, which means that you planned it, right? This is the way you wrote the program. You were supposed to end. And then it says, it's reached a termination state. And if you're unhappy because you did not plan it, it stopped, but unintentionally, then you usually call it a deadlock. Okay? So if the execution is finite, it's either a deadlock or termination, depending on whether you're happy or not. So let's see about this program. So we start with some state. This is the one initial state, satisfying the initial condition, right? C equals A, B equals B, and E equals 0. So this is one. There could be others, right? It's infinitely many states satisfying. This is just one execution or interleaving sequence, because the transitions here are going to be interleaved. Now, which transition I'm going to take? I look at what transition are enabled. C is bigger than 0. Yep, I can do this. or d is bigger than 0. I can also do that. Which one I take? I can take whatever. Right? I have a choice. It's called non-deterministic choice. Okay? I think all of you learned automata, right? You learned automata? So in automata theory, they told you that there is a non-deterministic automaton, right? And its language is equivalent to the language of deterministic automaton, etc., etc., etc. Okay? And here there's non-determinism too. Okay? But the point is that when you define non-deterministic automaton, a language of automaton was defined that if there exists an execution that accepts it, then it's in the language. So non-deterministic automata in automata theory was really nice. You could choose whatever, and if there was a good way to get to the final state, you were happy. Okay? Here, non-deterministic choice means that there are different executions. There are many executions, and the challenge is that all of them have to satisfy a property, right? So if you have non-deterministic choices, usually this is due to concurrency. It means lots of work. You have to check all of them, okay? So let's say in automata theory that in automata theory the non-determinism is angelic. It's good. It's like an engine. It's going to check non-deterministically a good path for you. And here it's a demonic non-deterministic. It's a bad non-determinism because maybe there is one execution which is good, which accepts, but you have to make sure that all of them, if you want to verify that the program works, all the executions have to work, right? So here non-determinism is not your angel, it's the thing that causes you headache. So let's follow this choice. And now after we did that, we decrement C, increment E, decrement C, increment E. Another time we can choose either this or that, right? Because C is still bigger than 1 and D is bigger than 1, right? So here let's choose this one. Again, we have two choices. We decrement D, increment E. Now we get to that state. Now there's only one transition which is enabled, because D is 0. This transition is not enabled, it's called disabled. This one is still enabled. We can decrement C again, and we get that state. And now we finish. E is equal to the value of A plus B, as this guy said, and we're happy. To verify that indeed that E at the end is the sum of A plus B, we have to check everything, that all the non-deterministic choices, with all the initial conditions, satisfy that. Okay? So let's go to something more realistic, our first real program. Okay? And unfortunately, our first real program is already concurrent, right? Just to make it fun. It's not interesting sequential code, right? So let's have fun and have concurrent. And now we have two processes. This is the first process. This is the second one. They're completely symmetric. And they have one shared variable, which is called term. And that variable could be either 0 or 1. The goal of this program is what's called mutual exclusion. You probably know it, right? Mutual exclusion. And the problem is that these two processes, they kind of compete with each other, but they cannot be at that label, CR here, CR here, at the same time. They're not allowed. That's our specification. We want to guarantee that. Okay? So I have that process, and first, everything is in a loop, right? There's an infinite loop here, symmetrically here. They are symmetric. This guy, what it does, it waits the term equals 0. And if term is equal 0, then it can progress. Otherwise it's stuck here. And here, what it does, it sets term to 1. So what happens is that they compete, but kind of they're gently. So they use the variable term to tell them which one can enter that part, which is called the critical section. That's why it's called critical. So only one of them can get at the same time into the critical section. That's the goal of this program. And if one gets to the critical section, then what it does is it sets, kind of complements the variable term, so it allows the other process to enter the critical section. So they alternate in entering the critical section. The code is clear? It's okay? It's very simple. Okay? Some countries, like the place I'm coming from, this algorithm would never work. People would not set the term to the other. So this is not a very smart algorithm in the sense that these, yes?
Is this H atomic?
That's a good question. I assume that everything is atomic. So when I'm going to model, it's because I assume it's atomic. It's not guaranteed in general. That's my assumption. So that's exactly when I'm, as the model person, is responsible. So I assume that for simplicity of this example, right? But it's a very good question, because you'll see that there's two ways to model this weight. Okay? I think that's what you have in mind, but you are about 10 slides ahead of me. So that's not, again, that's again the point of you're doing modeling. And the person who's doing modeling can make mistakes. The program is only verified as far as the model corresponds well with physics, right? And if I made a mistake in modeling, that may result in that I verified something, but it's wrong. If I find a counterexample and it's not a counterexample, that's not bad, because I could check and try that and it wouldn't be, I worked it. But if I said no errors and there is an error, then but you're right. So I decided that this is the way I'm going to model weight as an atomic action, and in this particular way, and that's not the only way to model it, and you're 10 slides ahead. Okay? We'll see. That's a very, very good. Okay? So the way I model it is the following. First of all, each process has its own program counter, and in order to make things simple, I made labels for every place that every value that the program counter can have, every place, right, in the code. Again, it's kind of artificial, but I called it L0. It's the head of the loop. And this process is going to be symmetric. L0, non-critical 0, critical 0. Okay? These are the values that are possible for program counter 0. And for program counter 1, I have these values. Okay? I have 3 transitions here that corresponds to that process, and 3 transitions here that corresponds to that process. Okay? Fine? So let's see. The first transition, what it does, it checks that the program counter is here. The program counter, it guarantees, as I said, that things happen sequentially or they branch according to the code. So I start, my initial condition is that the program counter 0 is here, program counter 1 is here. That's my initial condition. So at the beginning, program counter is 0, program counter 0 is L0, this condition. So the condition is that I'm here. I'm checking nothing about the value of the program counter, and the only thing I do is really very stupid. I just move from here to here. So I set the program counter 0 to non-critical. Right? So this is just a move from here to here. Now, if I'm here, I check that I'm here, right? Every transition, if I'm modeling code, checks something about the program counter and possibly something else. And changes something about the program counter and possibly something else, right? So I'm checking that I'm here, that's a part. But I'm also checking that term is 0. Only if I'm here and term is 0, I waited, and I assumed it atomic, just because I assume it. And hopefully this is consistent with the physical world. It's kind of a potential pitfall in modeling indeed. Because usually, if it was like an operating system, then a weight is going to be a very, very big thing, right? A weight in an operating system would include swapping out and into. I assume it's atomic. Then, if current is 0, then I'm advancing the program count. Notice that if I'm here and the turn is 1, then this transition does not fire. The labeling condition just doesn't hold. Okay? That's my assumption. I assume that it is like that. If you have some kind of problem with that, then you're right. But again, you're 10 slides ahead. And if I'm in the critical section, then all I have to do is I have to move back, right, in the critical section to the head of the loop. So I set the drawing counter to L0 again, but I also set the variable term to point to the other process so that the other process would. Okay? And do you agree that this is a model of that? Under my many assumptions, which may be correct or maybe not. Okay? So this is a simple modeling, and as you can see, because I used the program counter, these are just 6 transitions. I didn't have to, I mean, all the structure here, that I have a while, that I have concurrency, like all these are just transitions, and I'm going to select them according to the rules of my interleaving semantics, and that would correspond if I did not make any modeling errors. Under some assumption, that would correspond if I prove something about my model, that should correspond to proving something about the program. Any problems so far? Any questions? It's okay? As I said here, it's not the only reasonable way to model this program. And you'll see at least one model. So what I can do now is I can draw the state space of the program, which would include the states and also the transitions between the states. So these would be the initial states. The way I write initial state is I write an edge which enters that state from nowhere. That corresponds to this is initial state. I started here. Right? I can be here just because I started. I don't have a place in the slide, so I just list the value of the program counters PC0 and PC1. So just the first one would always be PC0 and the second one PC1. And if I can move from that state by firing T3, transition T3 in the previous slide, I'll be here. So I write it as this is the state where I am. This is what I can do, T3, and this is the resulting state after I do the so T3 currently is enabled here, and if I execute it, if I fire it, then I get to that state. And I can use a depth search algorithm that would start from initial states, and it would search all the way, and it would construct all the states, so it's the state graph that corresponds to the program. Now, what is very nice about this model is that this is a model that I can analyze. It's a finite model because I have a finite state system, and I assume this interleaving semantic, which is very simple. I think I kind of try to demonstrate the relationship between that model and what happened in reality. And I think kind of convincing that if I prove something here, that would in some sense correspond to what happened in reality, to some extent. And all I have to do is apply graph algorithms. So model checking would correspond to applying graph algorithm about this graph. I think this is very nice because you took a program, you can use a compiler to translate it into a transition system, and you can use a simple compiler, a simple depth of search, and you get that state graph, and you just need to analyze that graph against the specification, which is what we're going to learn. Let's see some points. First of all, from that state, I could fire, there were two enabled transitions, exactly two, T3 and T0. Okay? So there's a non-deterministic choice. A non-deterministic choice is caused here by concurrency, because both transition 0 and transition 0, process 1, and process 0, and transition T3 and process 1 could fire. Okay? If they are concurrent, if both of them can happen at the same time, then there is a non-deterministic choice. As we saw, we model it in the interleaving model as if they happen one after the other. Right? If they are really concurrent, then it doesn't matter in which order they happen. If they are not concurrent, right, there would be, in any case, some order between them, and the result of applying the one after the other would depend on their order. Okay? But then I can look at sequences here. The sequences here, let's see, this is a sequence, and that sequence corresponds to an interleaving, an execution. So a sequence in that graph would be an execution. Okay? All the states here are what we call reachable states. These are states that we can reach from the initial state by starting an initial state and firing transitions. Okay? Not all the states in the state space of the system are reachable. Okay? How do we know that? How many states we have here? 12. Right? How many states there are in the state space of the program? Sorry? Can someone think how many states there are, possibly? Let's calculate. The value of term has two values, two possible values. The variable of the program counter, how many values it can have? 3, right? L, NC, and CR with like 0, and the value of program counter 1 can have 3 values. So it's 2 times 3 times 3, 18. So I have 18 possible states, 18 states in the state space of the program, 12 states. What happened? The rest of the states are not reachable. You would never reach them. Okay? Is it good or is it bad? Do I want that? Is it possible? Is it important? But it's very, very important. Because let's see, what did I want about, I didn't tell you what the specification is formally, because we didn't learn how to write specification. But what did I want about this program? What was the goal of that program? Remember? What was the goal? I wanted to prevent what? Don't be shy. Sorry? Data race. Okay? That's tricky. But my goal was to prevent that both processes would get to the critical section at the same time. Right? That's called mutual exclusion. So I didn't want a state where PC0 is CR0 and PC1 is CR1. If that state was reachable, that was bad. Then the program did not satisfy its goal, right? So in fact, the whole thing is to prevent states like that. If I look here, these are all the reachable states. Is there a state where I look at the program counters, I have CR0 and CR1? No? Good? You see, it's good that I did not reach a state that I don't want. And because it's a small enough program, then I can verify it by looking at it, right? But because it has only 12 states. But of course, I'll have to show you how to do that algorithmically in case you have 2 million states. Okay? So these are important points which I will cover. And again, this is the specification, right? Mutual exclusion. And in that case, it's a specification very simple. It's something that says something about all the states. So it's called invariant. It's true about all the possible states, and that invariant is true. I can check it here just by looking, but usually by doing the depth search, and it's good. state where this health is not reachable. This is 0, this is 1 higher than this. Good? You understand so far? Someone wants me to repeat something, to ask something? Okay. Now I can ask something more complicated. The reason of using all this machinery would be maybe to say something more complicated. Like, if term equals 0, then at some point term equals 1. Any time the term equals 0, at some later time term equals 1. Okay? This is important because I don't want the process to be stuck, right? I want to say, I always give the permission to the other process as well, right? So that's another kind of specification. We will learn how to write it. But again, if I look at this graph, I can try, still I can do it with my eye, because it's a small enough graph, to see if it is satisfied or not. Is it satisfied? Someone knows yes, it is right. Why is it satisfied? I can see that if term is 0, then I'm in one of these states. Whatever I do, in any of these states, I go down, 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 down. And from here, I have to go to that side. And now term is 1. Now if I return and term is 0 again, I still have to go down and I'm here. So each time I'm on that side, I have to go to that side. This is kind of an informal description which I want to formalize. I want to formalize that property, to write it in the logic, and I want to formalize the algorithm to do that. That would be model check. If I can write that in logic and press a button, I'll get a translation of my program to transition system, and it would crunch, and it would say yes or no, and if not, it would be okay. If I look at the path here, say this path, it's an infinite path, and that corresponds to execution. Every path that starts in initial state goes on forever. It doesn't have to go on like that. So it doesn't have, this is actually a cycle, right? So it could go on, and one time it chooses that way, and another time it chooses that way, and then 3 more times choosing this path, and 7 more times that. But if it's an infinite path, and all the paths here, the maximum paths are infinite, there's no deadlock, there's no stop, then it is an execution. Okay? It's a path in the graph, and it starts with one initial step. So we know now what are the set of executions of the program, or of the model, and if I want to verify something, I want to verify not one of the paths satisfy my property, all of the paths. Okay? It's a very simple program. It's a very simple model. There's only 12 states. How many executions there are? How many executions? Are you counting? How many do you think? I mean, there are not a lot of choices here, right? So it could be, what do you say? Do we have more than, say, 6 executions? Oh, we go to the system of voting. Who says there are more than 6 executions? Okay. Who says there are less than 3 executions? Okay, you're very shy. So let me tell you how many executions, and infinitely many executions. Why? Because each time you're here, right? So in any case, if you go here, see, you go from here. So each time you're here, you have 2 choices. Each time you're here, you have 2 choices. 2 also, here you have 2 choices and 2 choices. So you can always make choices, right? So always you can make different choices. So there's infinitely many executions. Although there's only 12 states, there's infinitely many executions. And if you want to verify that the program satisfies the property, then all the executions have the satisfied. Here's infinitely. This is just a cycle, right? This is a cycle, but here I kind of unfolded it into an infinite sequence. Just have some information about that. Okay, let's go back to the error question. We said that the model I gave you maybe was not the only model. And now let me give you another model of execution. So I have the same program, but it could be that when I compile it on some machine, it executed in a different way and I did not model it correctly. In which way I didn't model it correctly? What that machine does is the following. Previously, I checked that if I'm here, I check, and if term equals 0, I progressed. Okay? If term did not equal 0, if I was here and term didn't equal 0, I simply did not do anything. This transition was not enabled. I didn't even waste a cycle. So in some sense, I assumed that there's something that would awake my program when term equals 0, and it would not consume cycles. There was no state. And here, it could be that I'm here, but I'm going to check. If term is 0, then I do that. But if term is 1, I'm going to just stay at the same place. I'm going to do, again, nothing much, but I'm going to consume a cycle, right? If, in programming, the previous model was called, please waiting. You wait, here it's called, I think, polling, in the sense that you're checking again and again. Is it 1? Is it 1? Is it 1? Each time you're checking. And you have to account for the time you check. Because if you're here and you're checking, then the other process is not doing something. You are doing it, right? Well, maybe you're doing it concurrently, but according to the interleaving model, there are two states, before and after. They are the same states, something happened, okay? It's a model, right? So you agree that this is a plausible model, right? I don't know which one is correct. It depends on how the system is actually implemented, right? In some systems, it could be implemented without the purple lines. In some systems, it really is going to check. Okay? If this is a system with only one process, if it's multi-programming, that means that this guy could actually interfere with the other, because this guy is going to check, and maybe it's going to check and check and check and check and check, and the other one is going to wait, but nothing happens. The other one is here, it wants to get into the section, it can, because term equals 1, but the system is really stupid, and it allows only that process to take the cycles. That's in multi-processing, right? So if it's multi-processing, it's really going to do that. So now I changed my model to correspond to the extra transitions, right? To the purple transition. In case that, so here and here, I can do T1 prime. See, T1 prime. So I'm here. Term is not 0. So what happened is that here, PC 0 is checking. Is term 1? No, I do nothing. It could loop here, right? You just stole a cycle. Here too, actually. Term is 0. So to check it, because it is in non-critical 0, right? And term is not. Term is 1. If it's in critical 0 and term is 1, then it does this. And this just is a self. This model is a self. Okay? So this is a different model. It will have different executions. Okay? And I don't know which model is true. That corresponds, I have to have insight of how things are implemented. That's exactly a pitfall if you're doing the modeling. You have to remember that. This is where if you model it in the previous way, okay, and you verify it, it could be that it's wrong. You know, what you verify is you verify the model, you're not verifying the system, and it depends if your modeling is good. Let's see something about this model. Now in this model, what would happen, as I said, is that I could have process 0, checking its value of turn, if turn is 0, and just looping, it just wastes the cycle. Or process 1, checking if turn is 1, it's not, so it's just looping. And hopefully at some point, process 0 would advance because it can. Here, process 0 would advance because it can. Okay? So there will be cycle stealing, and now I have an execution. I have extra executions that corresponds to these cycle stealing, and I can even have an infinite execution that goes like that. Turn is 0, okay? Now what happened is that process 0 moves from the top of the loop, which is non-critical. Process 1 moves from the top of the loop, which is non-critical label. Process 0 didn't move. Now process 1 tries to do something and it cannot because turn equals 0. It's not 1. So check. This turn 1 is checking nothing. Now I can do that again. Right? It's enabled. I can do that again and again and again. In fact, according to the model I gave you before, an execution in which process 1 moves one step and then it steals all the cycles, not progressing and not allowing the other process to move, is possible. This is consistent with my interleaving model, right? You agree with me? So my interleaving model has this weakness. Okay? It has this weakness that, you know, it's very simplistic. It says, start at the beginning, take an enabling condition, execute it, change the state, take another, take another, take another, take another, until you're deadlocked or indefinitely. And this is an execution. Also this one. I go here, I go here, tap, tap, tap. So what I'll have to do later is I'm going to have to describe the notion of fairness. I have to make the model a bit more complicated and tell you that an execution where two processes can do something, this would be just stealing a cycle, checking and doing nothing, like process 1. This would be a progress from L0 to NC0 by process 2. If I have the possibility of two processes to continue, and I only take one of them, that would be not fair. So there would be a definition of fairness on top of my model. And then if I want to verify the program, and this would correspond to the actual execution, that would be the right model, then possibly if the hardware is fair, then I'll have to exclude that execution and that execution. Okay? And so I would allow these transitions, but not indefinitely. So I have to make the model a bit more complicated. Okay? And the verification will take into account only the fair executions. And the last thing, I think, the last thing is a very important thing about model checking. If we look at these processes, so each process has its own variable, V1, V2, V3, n processes, and say they have 3 transitions. They just set the value of V1 to 1, 2, and 3 in the cycle. Okay? So if we do that in the cycle, how many states can you have? Right? So every state could have any value of V1 from 1 to 3, any value of V2 from 1 to 3, etc. If I have n states, how many values I can have? How many states I have? Sorry, if I have n processes, how many states do I have? 3 to the power n? 3 to the power of n. And this is called the combinatorial explosion. So the main thing, the main problem of model checking is that if you look at concurrent programs, you have a combinatorial explosion either in the number of processes or the number of variables. Then you have to think about complicated and sophisticated ways of not searching through all the states or searching through many states at the same time, or abstracting, taking a program and generating a smaller one which would satisfy the same purpose, or showing that there are equivalent relations and it's sufficient to check only several. And that's exactly why model checking is interesting, because you have this combinatorial explosion problem. So beginning, the first algorithm I'm going to show, it's just going to to be, very time wasting. This is a very simple example, right? It would take a lot of time. And then start to show you algorithms that are more efficient, that will take care of such situations. And there's always ways of doing research and coming up with more sophisticated algorithms. That's why it's interesting. There's always way of improving. Any questions from today? Okay, the slide should be available. Thank you.
大家等一会儿，然后我们这边用微信建一个群，大家点那个发起群聊，然后面对面借图，然后输个数字9527。
9527。
然后之后我们会把课件然后丢到这个群里面，然后如果有通知的话，也会在这个群里面发布。是白天不知道他们有没有今天打算讲。
那你跟老师说一下。
Let's say the first time.
OK。
就是说我们组团游的时候，我们组
那我们可以
对，
楼上有那种开
我还可以走。
这个新的不拿。
就是他们有的人还想要不知道，我正好我就是其他就有本校的就不用。那没办法，我一共就这么多，对吧？其他那个不是我们组的那个。